Up until about 5 years ago, this was UNC's largest telescope, Moorhead Observatory on campus. A number of you have seen it. Those of you who are taking the labs, which is about half of you or 2/3 of you, saw it on your first lab. And it's a nice telescope. Here's a picture of it inside, for those of you who haven't been there. It's a 24-inch. That's the size of the mirror. It's the mirror at the bottom of that tube. It's 2 feet across. Light comes in, bounces off the primary, comes back up, bounces off the secondary, comes down through a hole, so it's Casa-grain. And it's hard to see in the image, but you have a camera here at the bottom. You also have an eyepiece. On Friday nights, we have public nights. There's now a web page. Anyone can sign themselves up. It's free. Good date night kind of thing. And you can, there it is. And it's good for education and public outreach. We train some of our undergrads. We train some of our grad students on it. But it's not really a cutting-edge research telescope because the location, downtown Chapel Hill, is no good. North Carolina isn't a great place to build telescopes anyway. The weather's not optimal. We're not very high up. But here in the middle of the city with all the light pollution, it's not great for research. Still, I've seen cosmic explosions more than halfway across the observable universe with it. And we are getting it ready to go on Skynet. Probably within about 2 months, it'll be under full computer control. If you walk by it at night, you'll see the dome rotating. There won't be anyone there. It's just going to go over here, take images for some people, maybe in China, over here, some people in North Carolina, over here. It'll look at one of my cosmic explosions, and it'll be under full computer control. So it will become a little bit more research active, but it's not a cutting-edge research telescope. And this being our biggest telescope up to 5 years ago, we weren't really a cutting-edge research institution, at least not observationally. But this was all we had. And we have a handful of astronomers here. We've always done cutting-edge research, but usually on other people's telescopes or national facilities or spaceborne facilities or theoretical research. But we really wanted to be a cutting-edge observational astronomy institution as well. And so we started building other telescopes, mostly concentrated in the southern hemisphere. Certain advantages to being in the southern hemisphere. It's not, most of the landmass of the planet's in the northern hemisphere, so that's the part of the sky that's been studied exhaustively, at least historically. It hasn't been explored as much in the southern hemisphere because there are fewer telescopes there, so there's a lot of territory to explore. Also, if you're interested in, excuse me, galactic objects, the galactic center is a lot easier to see from the southern hemisphere. Up here in the north, in summer it gets kind of on the horizon, a little bit above the horizon, but if you go to the southern hemisphere, it's kind of high up in the sky and much more easily observed. There are all sorts of advantages to being in the south. So we decided to build an observational astronomy program in the south. We started building telescopes. We actually got to work on this long before 2004. That's when we dedicated our first big telescope. And they've been working on this, my colleagues, since I was 12 years old, actually. And so we've done 3 major expansions. In going from our largest telescope being the campus telescope, we now have more guaranteed access to the southern skies than any U.S. university. There's some U.S. institutions like the National Optical Astronomy Observatory that represents all the country, has more guaranteed access than we do, but compared to other universities, we have more guaranteed access to the southern sky than any other university. Now I'll show you the telescopes, but it's kind of interesting. If you go to places like Caltech, which has half the telescopes in the world, even if I was a postdoc there, even as a postdoc, you're fighting against the faculty just to get time on these facilities. There are a lot of people there, they all want access. It's hard for even a postdoc to get time, let alone a grad student. Forget it if you're an undergrad. But at a place like UNC, where we only have 6 or so faculty in astronomy, we had more, but had some retirements, and we have our current hiring freeze, so more time for the rest of us. And with all these new facilities that we're building, again, more guaranteed access than any other U.S. university, each faculty member in their group has tons of time. The grad students have tons of time, and even undergrads have a lot of access to our Crump telescopes that many of you are using in the labs, but can be used for a great many other things in cutting-edge research. And even SOAR here. We have undergrads observing with this telescope. So let me tell you a little bit about SOAR. It's a 4-meter diameter telescope And here it is. It's also in Chile. It's one mountain away from the prompt telescopes. And I'll zoom in here. It's kind of a small dome, but it's really packed in there tight. It uses all the space. So the mirror is 4 meters across. It's not the biggest telescope in the world. We know that the big telescopes are 10 meters or so. But from here to here is 4 meters. This was designed to be a very flexible telescope in terms of what it can do at any moment in time. There are a whole bunch of instruments, and you can change between them very quickly. Most major observatories, large telescopes, 10 meters, if you want to change instruments, you put it on the schedule. It takes a whole day to take an instrument off and put another instrument on and to switch between them. This can switch within a minute. So if my colleague's observing a galaxy using a particular instrument, and then a star explodes in a different part of the sky, and I'm notified of it, and I need a different instrument, I don't have to wait a day for the instrument to be changed. I can take over the telescope, change the instrument in a minute, and then begin my observations. And I'll just show you where all the instruments are. We're looking at the telescope from underneath. The light comes in from the top, bounces off the primary, which is hidden in here, but underneath here you can see the pistons. This is the bottom of all the different pistons and actuators that keep that mirror in a perfect parabolic shape. Comes up, bounces off the secondary, comes down, hits a tertiary. You got Naismith capability. You can send the light out to one side or the other. Over here we have UNC's Goodman spectrograph, built in Phillips Hall right next door down in the basement. It makes use of these VPH gratings, get really high efficiency throughput spectra, visible. On the other side we have infrared, near-infrared instruments. And near-infrared is kind of an exciting place to be working in, because if you're observing the far reaches of space, the far reaches of the universe, far back in time, after the Big Bang, that light that's being emitted, maybe it's emitted as visible light, it's traveling across the universe for billions of years before it gets to us. But during that time, the universe is expanding, and the light waves expand with the universe. There's no internal cohesion to a light wave. The universe expands, it expands too. So by the time it gets to us, it's in the infrared. So if you want to study the early universe, all the action's in the infrared. It's harder to do. The technology's much more challenging, but it's worth the investment if you want to study cosmic dawn. And that's a big push in astronomy, and a lot of the funding is being sent in that direction. So we have infrared instruments over here, and there are all sorts of other ports. That tertiary mirror can send it to all sorts of small custom instruments to do different things. It has all the active optics stuff that you would want, and an adaptive optics system being put on it as well. So it's very flexible. It can change instruments quickly, but you can also point to different parts of the sky very quickly. Rapidly saluting telescope. So if someone's observing something over here, and the star exploded over here, I study exploding stars. Those of you in the lab, read through lab 1, know a little bit about what I do. My exploding stars, they fade away really quickly. Every minute, every second really matters. So this was the perfect telescope for me, and it's one of the reasons I came to UNC back in 2002. It moves quickly, and you can change the instruments quickly. It's great for rapid follow-up of things that go bump in the night. So that's SOAR, Southern Observatory for Astrophysical Research in Chile. And it's a 4-meter workhorse. It does all sorts of things. It does microcosmic explosions, it does galaxies, quasars. They're using it to look for planets around nearby stars. It does a wide array of things. Sometimes by itself, sometimes in conjunction with other telescopes. And we can control it right here from Chapman Hall, the next building over. If you enter not that side, but that side of Chapman Hall, as soon as you come in, look to the left, there's a big glass window on the room. That's our remote ops room. And if you're in there in the evenings, some evenings, we're observing. We don't have 100% of the time on this telescope. This telescope was $35 million approximately, and we couldn't afford all of it. We're the founding partner. We designed it, but we can only afford like 17-18% of our own telescope. So we brought in partners. Brazil is a partner, the state and federal governments. Michigan State University has 14%, and the rest goes to the National Optical Astronomy Observatory, represents all U.S. astronomers, so any U.S. astronomer can apply for that fraction of the time. As can we, so we can get it on both sides, American time and UNC time. But when we do have our time scheduled, we're in that room observing, and undergrads often participate in this as well. So very exciting opportunity if you're interested in being a major or minor that you can get at UNC that you can't get at other places. Well, that's a 4-meter telescope, and sometimes the 4-meter telescope's just not enough.
Sometimes you need something a little bit bigger, and so we wanted to get into the 8-10 meter class telescope game, and we bought into this. This is called SOAR, South Africa Large Telescope. It's in South Africa, naturally. And this is a real picture except for the telescope that's drawn in. This is an older picture. They've since built it. I mean, clearly it's a drawing. There's a cutaway there. And what you have there is really poor construction. A tornado came by. Here it is. The mirror is actually like 11 meters from corner to corner. It's segmented. It's hard to make one piece of glass that big and transport it. So you can probably see it. There are a whole bunch of little hexagons that piece together. It's not a circular mirror. It's hexagonal. The Keck telescope's the same way. I think the Gemini telescopes are the largest circular single-piece mirrors, and they're 8 meters. And this is a poor man's Keck. The Keck telescope I can point anywhere in the sky. This, to save money, a big chunk of the cost in building a big telescope is moving that glass around precisely. You can't be crude about it, or else you don't know where you're pointed, or it flops around. Here, this thing, if this is the angle the telescope's at, I can move it like this, and azimuth. I just can't move it up and down in altitude. So we save a tremendous amount of cost. This would be a $100 million telescope. It's been built for $30 million. We're about a $1 million partner in it, so we're like a 3% partner in it. We're not the major effort here. But if you want to observe something, you have to wait. You wait until it gets high enough in the sky, corresponding to the angle that your telescope was built at. Once it gets there, you slide over, you observe it, and then it keeps going up, and then when it comes down, you slide back and you catch it again. You have to schedule things very carefully.
So it's really about scheduling. It's not good for things to go bump in the night. If something explodes and you only have a few minutes, the odds are it's not going to be at that right elevation, so I don't use it too much. But it's good if you want to do spectroscopy in particular, and you need a lot of light. This is a giant light bucket. Now, during that 1 hour, it's only perfectly aligned with the telescope, at just the height that the telescope's pointed for an instant. So, how does that work? And basically, you can't see it here, but the secondary is on a track. Here's the primary mirror. The secondary would be here, but you can slide it over this way or this way. If it's slid over in this direction, you're basically using this piece of the telescope over here. It's pointed over here. Or if you slide it this way, you're using this piece of the telescope over here. It's pointed over here. So you do have a little flexibility. You can look a little bit farther down than your fixed elevation or a little bit farther up than your fixed elevation. So over the course of an observation, if this is your hexagon, nope, that's going to be an octagon. There we go, here's a hexagon. So as an object is moving into position, and maybe it's coming across the mirror like this. Initially, we start by just using a small piece of the telescope, and eventually we're using the whole telescope, and then as it moves above, what we can do, we're using less and less of the telescope. On average, over this approximately 1 hour period, it's about a 9.2 meter diameter telescope, which makes it currently tied for 4th largest telescope in the world. So again, as I said, we're only we're only a small partner in this, a 3% partner. We do most of our work with SOAR, but occasionally we have need for something big, and we'll be able to use SALT 10, 11 nights a year. So it's a nice tool to have in your back pocket there. Okay, and then our third expansion is not in size, but in automated observing, and this is, of course, Prompt and Skynet. And again, those of you in the lab have had quite an extensive introduction to it, but I'll tell you a little bit about it here. So here's a picture of 4 of the original Prompt telescopes. There's 6 of them. They're in Chile, and they're small. They're 16 inches. So it's not really light-gathering power that we're going after here. What this is trying to explore and push is robotic observing, fully automated, no humans necessary. So it used to be if you want to observe in Chile, you'd get up, pack all your stuff, get on a plane, and you're gone for a week, and you have a 12-hour flight, and you're missing work, and it costs a lot of money. and that's how you'd observe in Chile. Now we can do some things remotely, like SOAR, we can use it remotely. We don't have to do that. We have our remote ops room, but still you have to stay up all night, and then the next day, young people can do it, but us older people, we function not as well the next day, and our lectures kind of suck. And so this is the future. I can just go to the web page and say, I want to observe this, and then I go to sleep. And then the next day, there it is. So it's kind of exciting. But it's really difficult to do. Lots of people have these robotic telescopes. They have like one robotic telescope that they built, and they built their custom software for it. And maybe the telescope breaks once a week, and they log on and they fix it. You can fix most things remotely. You don't have to be there. Maybe software malfunctioned, or Windows updated and it's offline, or something like that. Well, if you have 7 telescopes, then that's once a night. If you want to build a global network with 70 telescopes, that's 10 times a night. And you're going to have many employees just constantly fixing things. And so that's no good. And where we've really succeeded, we're kind of the leaders of this here at UNC, in the Skynet software that we've developed to control these telescopes and now other telescopes. We've identified all the ways they can break. Each and every hardware component, the telescopes, the mounts, the cameras, filter wheels, we know how every screw works and doesn't work, and all the pieces of software, some that we've written and some that are commercial. We know all the ways they break, and we've built Skynet to correct automatically. And most of the stuff we don't even have to worry about. Skynet can detect the failure, it fixes it, and if it can't fix it, it rings their cell phones, and we jump on and use our human brains to try to do what Skynet couldn't do. But it's pretty rare. In terms of physical malfunction, we have to send someone up here maybe once a month. And we got 6 scopes, and we're about to have 8 scopes there. So that's really good success rate, and we're making it possible. It's possible to move to the next level, expansion into a global network, which I'll talk a little bit about in a second. Here I am, looking awesome, and here's the telescopes up close. You got the primary mirror, the secondary, and the camera. Nothing fancy, but it works without humans, and that's what's exciting. And the idea is that maybe we can make bigger telescopes work this way, bigger and bigger and bigger, and more and more and more. So I built the telescopes originally to go after these cosmic explosions. They now do a wide variety of things, but the original funding came from the National Science Foundation. This is just a picture of one of them. This one went off in 2008. It's the most luminous thing ever observed. The prompt was on it within 32 seconds of the explosion being detected in orbit by NASA spacecraft. They're called gamma ray bursts. They're stars that are about 25, 30 times more massive than the sun. Although they have a lot of fuel, they burn it more quickly, so they live hard and die young. And they die almost as soon as they're born, cosmically speaking. And they blow up, and we won't talk about the mechanism. For that, you have to take 102. We talk about these and other things. But they spit out all the radiation in a tight beam, all the light. If it's pointed at us, it can be incredibly bright, even if it's incredibly distant. Like this thing was over halfway across the observable universe. Yet if you looked at the right part of the sky at the right time, it was actually naked eye brightness, which is a first for these. But the other ones are often not far from that. So very exciting. You can use them as probes of the faraway universe. And there's studies of stars exploding and black holes forming. We're actually watching a black hole form seconds after it was born, so that's kind of cool. Seconds after the star died. But they fade away pretty quickly, and so although these spacecraft that detect them about once every 3 days, there's a lot of downtime, and so we use the downtime for a great many other things. We made it available to not just my colleagues here at UNC, but to 12 undergraduate institutions across the state. They've been doing all sorts of stuff with it, non-PhD institutions. So mostly they're doing educational work, but also they're doing research and publishing papers on all sorts of things that are variable. And these telescopes are great for variable astronomy. So like rotating asteroids or binary or trinary asteroids, quasars, all sorts of variable stars, pulsating stars, supernova explosions, things that change the brightness and are quite bright, bright enough to see with a small telescope. These are ideal for it. And this is just kind of a Google Analytics map. It's, if you have a web page, you stick in one line and Google will keep track of every IP address that ever comes to it. So it's free, so we do it and get statistics on who's using our telescopes, and they're very broadly used. And of course, they're being used educationally as well in the labs. The labs are now designed around them. Those of you in the labs, has it been a good experience? You've enjoyed it? So you're not going to find a non-major undergraduate experience like this at any other university. So it's kind of a cool thing, and I hope you're enjoying it. It's new. We're still working out some of the bugs in the labs, but I think it's exciting. Also, Chile gets 10% of the time. So they use the telescopes. Moorhead Planetarium gets 10% of the time. They use the telescopes in North Carolina high schools. Thousands of high school students have used it. 20,000 visitors to the planetarium have used a simple interface that is described. If you go to the ebook, and look at the exercise, and give you a link to use the simple interface. If you're not in the labs, you can put in an observation yourself without really needing to know how all the details work. So it's being used by tens of thousands of people, and we're really excited about that. And a lot of this was made possible because we had a big discovery using SOAR and using prompt in 2005. We found the most distant explosion in the universe, at least at that point in time. Held the record for 3 years. It's a star that exploded 12.8 billion years ago. And, it exploded, the light started traveling across the universe, Earth formed, kept traveling across the universe. Humans evolved, we built telescopes, and then the light came by. And I happened to grab it, and an undergrad was working with me, and we published in Nature, kind of the most prestigious journal. The undergrad, junior, got to be first author of the publication, so that doesn't happen very often. And we held the record for 3 years, got a lot of funding, and it enabled us to do all these exciting things with Skynet. But then we were running short of money, and we went back to the National Science Foundation and said we need more money. And they said, well, you're in luck, the economy's just tanked, and so there's the Stimulus Act. And they got a little piece of the stimulus funding, and they made it available for instrumentation programs. And I said, okay, I don't really want to build more telescopes, but if that's where the money is, that's what I'll do. And I asked for $2 million, and I got it. So thank you, taxpayers. And so we're expanding Skynet in 3 ways. Exciting developments occurring, so I'm going to tell you a little bit about those. This is an aerial shot of Tololo. Up here we have a 4 meter, not SOAR, a different older 4 meter, and some 1 and 2 meters. And these are human controlled, either at the telescope or remotely. These look small and piddly, but they're computer controlled. I get to sleep, and these people stay awake, so that's the difference. Again, prototype technology that hopefully someday all the telescopes will be using. We have an X here because we're expanding, we're adding a telescope, actually 2 telescopes. I'll mention the newer one because it wasn't part of the Stimulus Act. The Kingdom of Thailand has partnered with us, and they're paying to build a 24-inch polarimeter. We talked about polarimetry. You can measure the orientation of the incoming light waves. So we're building an exciting, it'd be the world's fastest robotic polarimeter, and that's going up this year. And then with the Stimulus Act, we got money to build a 32-inch. So Moorhead Observatory is a 24-inch, so it'd be bigger mirror than Moorhead Observatory. Here's a schematic of it. It doesn't look big because they're made really compact these days, but that's a pretty big mirror. Got a person next to it for scale. The enclosure's there. If you go to the Skynet website and go to prompt cam, you can look at the telescopes, you can pan around, zoom around the site, you can see the enclosure that we've built. Telescope is now ready. This picture is just a couple days old. We partnered with some Europeans, owner of a telescope making company. They're donating the telescope, $500,000 telescope. And the trade-off is they get to use it half the time, and he's just going to make pretty pictures with it. The other half of the time I'll be using it, and my collaboration will be using it for science. And if something explodes, I get to take it over. But it's a bulky, hefty telescope. You can't tell because there's no person standing next to it for scale, but we're excited about that. And there's going to be all sorts of nifty instrumentation on there. There's going to be a wide field camera for making big, pretty pictures. It's going to be a Lucky Cam, which is kind of relevant to what we talked about. It's a high-speed camera you only use on bright things like Jupiter. You take images faster than the time scale over which the atmosphere is changing. Throw away all the bad ones, maybe 1% you keep, and it's like there's no atmosphere. So it's used kind of for Jupiter and Venus atmospheric observations. And then for me, I'll be putting this instrument on. This is an infrared, near-infrared camera. As I said, most of the cutting-edge stuff, If you want to study cosmic dawn, you got to look in the near infrared. But it's challenging because here's an infrared camera just sitting there. It's emitting more infrared and detecting itself more easily than it can detect light coming from space, because we're all emitting in the infrared. So to make this work, you got to cool it down with liquid nitrogen, and this camera is designed to withstand liquid nitrogen temperatures. It makes it expensive. It's a $150,000 camera. And guess how many megapixels that buys me? $150,000. 1/16 of a megapixel in the infrared. So it says 256 by 256, but it will be able to do infrared on the rapid timescale robotically. So we're working on that now. As part one of the Stimulus Act, part two is we get to expand our location geographically. So we have this big cluster in Chile. We also have volunteer telescopes across the US and now also in Italy that have joined Skynet, and you might see them online some nights. And their connectedness to Skynet's improving with time. But we have nothing on the other side of the world, and we really wanted something at the same latitude as the Prompt telescopes in Chile. So when Prompt can't see it anymore, because the sun's coming up, we can hand off to Australia, and they can pick it up and observe, and we can have near continuous observing, which is good for all sorts of things, but particularly for stars that pulsate very quickly. You don't want very many gaps in your observing. And that's going to be possible. We're building another cluster at the National Observatory at Siding Spring in Australia. So we've had our first trip out there, and those will be coming up this year as well. And they're going to look pretty much like the Prompt telescopes. Nothing fancy here. There'll be 4 of them. And when not being used for science, there will be a kind of a cheap infrared camera on one of them, $25,000 cheap, but when not being used for science, Moorhead Planetarium is going to have access to them. They're going to gut one of the rooms and make a walk-in live observing center. Because when it's daytime here, it's nighttime there. So anyone will be able to walk in off the street and start observing in Australia. I don't know if it'll look like that. That's an artist's rendering of what it might look like. But the idea is within 30 seconds, they get to hear the telescope move and they get their image back. Okay, and then the final part here, which leads us into radio astronomy, which is the next unit, is, well, a radio telescope, our third expansion. Right here we have the transparency of the atmosphere in all sorts of different wavelengths. Radio on the right now, and you got infrared, and visible and ultraviolet, and X-rays and gamma rays would be off the left. You can see there are only 2 windows really where light makes it through.
Clearly we have a window in the optical where it's 100% transparent. And so we go off into the near infrared, meaning infrared close to the optical. It's kind of wavering, it's come and go, but we can do some science from the ground. And then in any other wavelength we can't except in the radio. Radio waves come through the atmosphere as well. And so we propose to expand Skynet to handle radio telescopes. These are these things. So this will be going on Skynet over the next 3 years. That's a door at the bottom, just to give you an idea of scale. The dish is 20 meters across. Radio telescopes look very different than optical telescopes, but same idea, reflecting surface and a prime focus receiver. And so we're expanding into the radio, and you'll be able to control this through the same Skynet interface. See? Okay. Anyway, I'm going to stop there. So that little segment there was UNC's telescopes, to focus on the ones I'm involved in the most. Any questions on any of that? Okay. So, as I said, 5 years ago, our largest telescope was Moorhead. Now we have all these facilities. We have more facilities per faculty member than, I think, anywhere. So it really is now strong, up-and-coming, even leading institution in the field of astronomy. Exciting place to be, exciting times to be here as an astronomer.